Want to be popular in your group? Let me show you a magic trick. It's very easy. All you need is one coin, a bowl and water. First of all, keep the coin in the bowl. And if you see from this angle, you can't see the coin in the bowl, right? But notice what happens when I pour water in the bowl. Well, you can see the coin. That's the magic or science. I always tell you, magic only seems like magic until you understand the science behind it. So let's understand the science behind it. Welcome 10th graders and especially welcome to the ICSE students, because today we are officially announcing that I'll be teaching ICSE also. Today we are taking the topic of refraction of light, grade 10th. Real and apparent depth. Now, class 10th light anyways we are covering for CBSE, not a problem. But this video is specially to people who want to understand about real depth and apparent depth, right? It's a very nice, very important concept, which is my favorite. Yes, I like this concept. You know, in this session, we'll be understanding the formula. Yes, we'll be deriving the formula. Yes, we'll be differentiating between which wavelength will have more real depth, more apparent depth. That also will take care of. Don't you worry about that. So today, welcome. Let's understand this. Now, let's start with what we see around us. All right. For that, I'll just make myself a little smaller over here. Can you please make myself smaller? Nice. That's better. Whenever you go for your swimming lessons or you look in a pond or wherever, right, you notice that this floor of the swimming pool, it looks a little shallower, right? That's true, because this is what we have been seeing. And what you saw in the starting, it showed you the same thing. Means there is science behind it. It's just we don't know yet. Let's understand that. This is the concept of real depth and apparent depth. So whenever you see something which is kept inside a denser medium and you are looking from, the rarer medium, you see that thing looks little raised. Be it something inside the water, be it something, let's say you make a point on your notebook and you keep a glass slab over it. It also looks a little raised, Same thing. But why and how? This is something let's talk about. See, first of all, let's talk about two important terminologies. The actual depth of the object kept from the surface of the denser medium, right? It's called the real depth, and which is actually fine. Real depth or actual depth, that's just potato, right? That's not a problem. This is the actual depth, means from the surface of the liquid till the point where the object is actually kept. That is the actual depth, or you can say real depth. Then the point where you see it, which is actually, it looks a little raised, no? So that is something where the object seems like it's there, but it's not. It's something which is apparent to you. It's not the real thing. It seems like, right? So it's an apparent depth. We call it the apparent depth. All right. So this is apparent depth. This is the actual depth, h, and this is small h. Fine. All right. Depends on you. Whatever terminology, whatever symbol you want to take, that's on you. Not a problem. All right. Is this terminology clear? Real depth and actual depth are same thing. Apparent depth is something where you see the object. It's an illusion. Fine. Now, what happens? First of all, let's see ray diagram accordingly, right? Look, when do you see anything? You see anything when light from that object reaches your eyes. Simple. So light from this object is trying to reach your eyes, but what is the problem? In between, it found an interface, the interface of water to air, because light is going from water to air, means it is going to bend away from normal. All right, so it bent away from normal like this. If you notice, this angle is lesser compared to this angle. Angle of incidence is less than compared to angle of refraction. Correct? बहुत सही. अब ध्यान से देखो. So now this light ray is traveling, and it reaches your eyes. Now we all know that our eyes along with our brain have this tendency to imagine or assume that light travels in a straight line. So this is where the image you will see, correct? Yes. Why? Because the straight line will not bend anywhere, right? So what will happen? Your brain will give you this illusion that the actual position of the object is over here. Why did this happen? This happened because of this, the bending of light, because of refraction, alright? So, light would have gone straight, but it actually bent, and if you trace it backwards, you will see it is meeting this vertical ray over this point, and this is where the apparent depth would look like to be, which is lesser compared to the real depth. Very good. Alright, bahut achhe. Can we derive this formula? Yes, we can. Alright, let's discuss about this. Real depth and apparent depth. Very good. This is my real depth. This is my apparent depth. For that, let's take a few things into account. The first is, u is, let's say, the actual object distance. Here is u. Correct? Alright. Everybody, I want you to note down if you really want to understand this derivation, okay? V is the apparent object distance. So let me choose something else. This is V, the apparent thing, no? This is my V over here. Very good. Alright. Mu1 is the refractive index of medium 1. Alright. This is my medium 1, let's say. And 2 is the refractive index of medium 2. This is the refractive index of medium 2. Alright. So what we have given you? We have given you the absolute refractive indices. Very good. Let me ask you something. What is the refractive index? When light travels, let's say from medium 2 to medium 1, if this is my point, light is traveling from this medium into that medium, it will bend, that's fine. This is going to be I, let's say this is going to be R, alright, because this is the arrow. What is going to be the refractive index of medium 2 with respect to medium 1? What I'm asking? Mu 2, 1, right? This is what I'm asking, or mu 2 upon mu 1. This is my question. Come on. I have taught Snell's law. Means you understand this, everybody. Come on. Focus. Mu 2 upon mu 1. Apply very simply the Snell's law. Dhyan se dekho. It's very easy. Come on. See, what did I say? I said, if you want to apply Snell's law, just do these two things. First of all, sine of the angle in the medium, means let's say sine of R multiplied by refractive index of that medium in which that angle lies. So R lies in medium 1, alright, into mu 1 is equal to sine of the other angle, that is sine of I, is into multiplied by refractive index in which that other angle lies. So I is lying in medium 2, right? So this is medium 2. What do you want to find? You want to find mu 2 upon mu 1. So what will you do? You'll just take mu 1 this side and sine that side. So what do you get? Sine of R upon sine of I is equal to mu 2 upon mu 1. Tell me, this is clear or not? Snell's law becomes very easy if you use this method, okay? Please use this method. I don't want any one of you to make this silly mistakes, okay? Alright, come on, let's move forward now. So this is clear, sine R upon sine I is mu 2 upon mu 1. So notice over here, if I mark, let's say these 2 points over here, this, my friend, is I, okay? This is R. So what I'm saying is that sine of R upon sine of I is mu 2 1, correct? Alright, perfect. So mu 2 1 we have found. Now, there's one approximation which comes into picture, and that approximation troubles you a lot. That approximation says, hear me out first, if this I and this R are very small angles, right? If they are very small angles, we can say that sine I is almost equal to angle I is almost equal to tan of I. So I would suggest you forget about the middle one for a while. Just see, sine of I becomes almost equal to tan of I if angles are very small. Now, you tell me something. Do you understand this? Many of you don't understand this, because when I'm also from ICSE board, and I also have this problem sometimes that suddenly you say approximate, let's take this much, this angle is very small, which means the hypotenuse will be equal to the base. Why? I mean, can somebody explain me that? Let's try. And you know what? This is where simulation can help us a lot. Focus over here. See, this is one circle. All right, not a problem. Now, let me show you something. If let's say this is one circle, all right, and this is the center, this is O, all right. Now, if let's say you have your point A over here, this is my radius of the circle, this is the perpendicular, and this is the base. So hypotenuse is the radius, base is marked over here, and this is the perpendicular. All right, clear, right? This is perpendicular, this is base. Very good. Now this angle is, let's say, theta. Sine of theta is equal to perpendicular upon hypotenuse. All right, means perpendicular upon radius. Very good. Cos, forget about cos, tan of theta is equal to perpendicular upon base. Clear? All right, now notice this triangle. Look at this triangle. See, when I reduce this angle, what I'm doing, I'm bringing this point closer and closer and closer to this point, right? What am I doing? I'm bringing this point A and this point B very close to each other, correct? Yes. Now notice, right now this here is the hypotenuse, this here is the base, all right, but perpendicular and arc both are two different things. Okay, now focus over here, and this is where it gets very, very interesting. When you move this point closer and closer to this bottom point, the second point, what do you see? The arc and perpendicular both become equal. When both become equal, do you notice? If I bring these 2 points very close to each other, there is no difference between radius, which was the hypotenuse, and the base. Means the hypotenuse becomes equal to the base if the angle is small, and perpendicular becomes the arc length. As simple as that, okay? So at least to prove that sine theta is equal to tan theta for very small angles, we just have to prove that base becomes equal to hypotenuse, which right now, my friends, you are able to see because there's a simulation which you also can try sitting at your home. The link I'll give you in the description, not a problem with that, okay? Let's move further. If perpendicular is equal to the base, now notice, if this angle is I, okay, if this is I, this is going to be I. Why? Interior alternate angles. Very good. If this is R, let me mark this with a separate color. This complete angle is going to be R. Vertically opposite angles, right? Now, if this is R, means this is also going to be our interior alternate angles, right? Because this is perpendicular and this is perpendicular, both are normal. Okay, fine, all right, don't be confused. See, derivations, please don't be scared. Derivations, they are very easy. You have to practice them with yourself, right? That's a must do, right? You have to do that, and you have to promise me right now. Okay, everybody, if you're understanding everything right now, please like the session. I just tend to forget that. Okay, now notice, all right, this is done. So one triangle is this, and one triangle is this one. Okay, all right. Now sine of I, everybody focus. Sine of I is how much? Sine of I is x, which is over here, perpendicular, okay, perpendicular upon hypotenuse, right? Hypotenuse, let's say the hypotenuse is, what do I say? Let's say hypotenuse is z. Nobody uses z, let's use z, okay? X upon z. This is sine of I. Tan of I will be how much? Tan of I will be, come on, think about it. Tan of I will be perpendicular, that is x, upon base. Base is u. Now, we just said if angles are very small, the base and the hypotenuse becomes equal, right? Means u is almost equal to z. Means sin I is equal to tan I, right? So, the formula of refractive index, what can I say? So, this thing I'm writing over here. For small angles, sin I is almost equal to tan I. Okay, so formula will become this: tan of R upon tan of I is equal to mu to 1. So tan of I is x upon u. Alright, what is tan upon R? Same logic, tan upon R. Tan upon R is perpendicular, that is x. Tan of R is equal to perpendicular, that is x over here, because this here is R. This, my friend, is the triangle. Okay, this is the triangle, perpendicular is x, base is v, which is the apparent depth. So tan I upon tan R becomes how much? Tan R is x upon v, tan I is x upon u is equal to mu to 1. So what do you get? X and x gets cancelled, so it becomes u upon v is equal to mu to 1. So can we say it is real depth upon apparent depth? That's the derivation. Okay, simulations are powerful. That's how we learn. The people who learn at BYJU'S, right? If you love this kind of a learning, please subscribe to the channel and like this video, because that's important. All right, now let's move further. So apparent depth, what did we learn till now? The apparent depth depends upon the depth of the liquid. Sir, how do you know? All right. Look at this formula, no? The apparent depth, that is V, depends on the real depth. How? If you take it over there, if refractive index is constant, it becomes, right? The apparent depth depends on the depth of the liquid. Means if you have less water in the beaker, the rays will be smaller. If you see this much, let me change the color. This much is the total change in the depth, okay? This much is the total shift. But if you have more water in the beaker, means the real depth is more, because this is the real depth, no? The shift is also more. So the apparent depth depends on the depth of the liquid. All right, first point, greater the real depth of the object, the more will be the apparent height of the object. Yes, all right. The apparent height of the object from the base, basically. So if you want to ask the apparent depth from the surface, it will be smaller, right? So greater the real depth, smaller will be the apparent depth, you can say, right? And apparent height is something, kids, this is apparent height. So, okay, don't be confused with the lingo over here. I'm telling you, apparent height, if this is my real depth, how much above it the apparent position is, this is the apparent height. But from the level of water, how deep this apparent position is, this is the apparent depth. So if real depth increases, the apparent depth decreases. Why? Because the object is kind of, the apparent position is moving closer and closer to the surface, no? So apparent depth decreases, apparent height increases. Clear? Don't be confused. Greater the real depth, apparent height will be more, apparent depth will be less. All right, clear? All right, chalo, let's move forward. Now, this is something we can say it's true for everything, right? Means it's true for light, but light every time is not just one wavelength. White color is a spectrum, right? White color is a spectrum where we have VIBGYOR, violet, indigo, blue, green, yellow, orange, red, right? Okay. Now, what if I tell you, and this is again very important thing, बहुत ध्यान से सुनना बच्चों. This is very important. The real depth and apparent depth will be different for different colors. All right. What am I saying? Apparent height. What is apparent height? I hope now all of you understand. This is my real object. This is my apparent object, and this here is my surface of water, or let's say any liquid or any medium. Okay. This is apparent depth, this is apparent height, and this total distance is real depth or actual depth. Okay, don't be confused. So what I'm saying, for the red color, the apparent height is the least, or for the red color, the apparent depth is the most. Okay, for violet color, the shift is more, means apparent height is more, means apparent depth is less. Clear है ना? ध्यान से देखो, if you pour, let's say, if you have a violet colored dot and over that you have water, the violet colored dot will raise more compared to the red colored dot. Why? Because violet color will bend more. Whoever bends more will show you greater shift. This shift was happening because of bending of light. Who will bend more? Shorter wavelength, right? So violet bends more, red bends the least in the visible spectrum, right? So violet will give you greater shift. इसमें रटने की ज़रूरत थोड़ी है. It's very easy. Now I can prove it to you using mathematics also. It's not a very rocket sciencey thing. Refractive index of the liquid is what? Real depth upon apparent depth. Not a problem. Very good. So real depth is, let's say, h, and apparent depth is, let's say, h dash. Alright, not a problem. So this is my real depth from the surface. This is h, and this here is my apparent depth. This here is, let's say, h dash. Alright, not a problem. And real depth is more than apparent depth, so h upon h dash will be more than 1. We understand this. Not a problem. So h dash is inversely proportional to mu's. How? This mu you have taken over here, and this h dash you have taken over here. कुछ नहीं किया, इधर उधर कर दिया बस, और क्या, right? So h dash is proportional to mu. Why? Because real depth is constant. You are not changing that. Okay, fine. Now, refractive index for red color is different than the violet color. Refractive index for red is actually lesser compared to the violet color, because I told you violet bends more. जो ज़्यादा bend होता है उसका refractive index ज़्यादा होता है. As simple as that. And you know what? It's mathematical also. It's not very rocket sciencey. What is mu? Mu is C upon V, right? I can say mu lambda upon mu lambda 2, right? So mu is proportional to lambda, correct? So higher wavelength, right? So mu is inversely proportional to lambda, by the way. Sorry, my bad. Mu is equal to frequency into lambda 1, which is wavelength in air, upon mu into lambda of the medium. So mu is inversely proportional to lambda. So for higher wavelength, the refractive index is less. For lower wavelength, the refractive index is going to be more. Alright. So what can we say? Mu of R is less than mu of violet. Clear? Because violet bends more, it has more refractive index. H dash R is going to be more than H dash of V if refractive index is more. Why? Refractive index is inversely proportional to apparent depth. If refractive index is more, the apparent depth is going to be less. Means apparent height is going to be more. Means more shifting will happen. So that is why H dash of V is less compared to H dash of R. This here, wait, let me mark it with a separate color. This here is the H dash of R, and this here is the H dash of V. So H dash of R is more than H dash of V. Very simple, है ना? Don't get stuck in only mathematics. Use your logic. Who bends more? Violet bends more. The one that bends more, it will give you more shifting, right? So that's why violet will have more shift. It will have lesser apparent depth. Very easy. Now, let's just sum everything up. Factors affecting apparent depth. Very important. Higher the refractive index, more is the shift. जो ज़्यादा bend करेगा, ज़्यादा shift होगा. Very simple. Greater the real depth, more is the shift. जो ज़्यादा deep होगा, उसमें shifting ज़्यादा होगी. Very easy. Shift decreases with increase in the wavelength of the light used. Actually, first point and third point are actually the same thing, just other way of saying the first point. Last point is saying shift decreases with increase in wavelength. Means red color will shift less. We all know that, right? Who bends more will shift more. Easy. So in your poem, the poem which I keep on telling you every time, red bends the least. It will shift the least. It will scatter the least. For ICSE, this one is important, okay? Red bends the least, scatters the least, and shifts the least in real apparent depth. Violet bends the most, scatters the most, and shifts the most in real and apparent depth. Easy, alright? So, with this, the important formula, at least for your grade, becomes refractive index is what? Actual depth upon apparent depth. When you look at the object from the rarer medium. And you know what? This formula is not something you can't remember. Why? Think about it. Refractive index of a denser medium with respect to rarer medium, it's going to be more than 1. In real and apparent depth, which one is more? So real depth. Who should be in the numerator? Real depth. So real depth upon apparent depth. Very simple. Okay. Alright. So this is, my friends, important formula. You can write it like this U mu 2 1 also for ICSE because you are more familiar with mu. Not a problem. So with this we are done. Now I have a question for you. Can you give me the formula, or forget about formula, you tell me what will happen when you look from the denser medium into something in the rarer medium? What will happen and why? That is my homework to you, right? Come on, tell me. And if you love what we do over here for you, subscribe right now, because I'm telling you, out there is a lot of noise, there is a lot of cacophony, there is a lot of shouting here and there. But what I'm saying is, if you really believe in quality content and you think after 1 or 2 sessions, this is what we give you, subscribe. Otherwise, it's fine. You're free to go anywhere you want, right? And like this session, because everything that we are doing here, it takes, I would say, motivation, dedication. And how will you motivate someone to do something? Just praising them. Do baatein, hai na? Like, this is one way of telling the team that, you know what, we appreciate what you do, like right now. Apart from that, share it with your friends, because for ICSE also, we are here. Relax and subscribe to the channel. I told you already, and like this video. See you next time, and I hope you understand that magic is only magic until you understand the science behind it. See you next time. Take care. Bye-bye.